I am talking about polymers. Polymers are everywhere, and most of the conveniences we enjoy today are due to polymers. There are two kinds of polymers depending on the linkages, the strength of the linkages between the links. Actually, these are links. The one on the left side is the links, and that makes the chain. How these chains are connected is depend on the strength of this bond, actually, or the interaction. If it is very strong, we say it's covalent bond, and we get normal covalent polymer. And we usually synthesize them in a solution, and as a result of which you get a random polymer. Actually, there is no order for the polymeric chain we get. And there are other kind of polymer which is called non-covalent polymer, in which the interaction between these links are very weak interactions, but there is the polymer which results from this will be highly ordered. So there is orderness in such polymers, but they are very fragile polymers because of this weaker interaction. And there are properties due to this orderness, and which will come. So these are the molecules we start with. Actually, these are simple sugar molecules. The first one is glucose, the next one is inositol, the third one is mannitol. These are highly hydrophilic molecules. They easily dissolve in water. So we don't want such molecules. What we do is we modify them. We modify by attaching hydrophobic or water hating functionalities and make them amphiphilic, so that they will dissolve in solvents other than water, like hydrophobic or non-polar solvents. When we dissolve in such non-polar solvents, they start to aggregate because of this hydrogen bonding, a weak interaction, weak non-covalent interaction, to make this schematic which I have shown like a dumbbell. So they will arrange like a fibril, actually. They will arrange like a chain through this weak interaction. And such a fibril again aggregate further to give bigger fibers, and they will entangle like a spaghetti-like network, and within which the solvent in which it is self-assembling will get trapped, and that leads to a gel, actually. So that is a mechanism for gelation. And these gels have a lot of properties and applications, which I'll come to. Next slide, please. Yeah, so this is one of such molecules we have made. This is out of mannitol and acetone. And this is a good gelator for many oils. The oils are very interesting because they have a refractive index of glass, actually, 1.5. They are transparent and they have refractive index like glass. So they can be a glass substitute. For example, water cannot be a glass substitute because the refractive index is so poor, though it is very transparent. So we thought we can, since we have a gelator which can congeal or which can make gel of different oils, we can use them as soft optics, actually. So next slide, please. So yeah, we have made different oil gels. These gels are nothing but different oils using our gelator, and this is a self-healing gel. That what I meant by that is, if I cut this gel into several pieces and put them together, after some time you see a seamless gel piece, actually. So we have made different objects like this kind of hinges, the cubes, cones, towers, etc. And also we have made prism like this one. So by pouring a hot solution of this oil into this this cavity which made out of three glass slides. And if you remove the glass slide, after some time what you get is a prism. And you can see it is a functional prism. You can see the Vigier pattern. Similarly, if you put this in a planar convex plate, if you put in a watch glass, actually you get a planar convex lens. And if you put two such planar convex lens, what you get is a double convex lens, which is again functional. You can see the magnification of my name in that paper. Next slide, please. So this is basically a soft optics. Another application of gelator is to use them for oil spill recovery. There is a lot of interest in materials which can congeal oil from oil-water mixture. So such materials are called phase selective gelator. That means they selectively gelate the oil layer. So these materials are proposed to have application in marine oil spill recovery. There is a lot of interest in such material which can congeal crude oil, for example. That will be useful for marine oil spill recovery. So we have made this particular gelator, and we have shown in a laboratory setup, this is a mixture of petrol and water, and we could selectively take out all the petrol from this water mixture. Then in the real life scenario, it's not petrol what we find in marine oil spill. It's the real crude oil. Later we found that crude oil also can be gelated by using one of our material. This is a sugar derived material where we can directly add as powder. Still there is a problem because what you get is a jelly mass, and you are talking about square kilometers, hundreds of square kilometers of sea surface. How do you take out this jelly mass is a big question. So to address that, we have impregnated this material in a cavity. So next slide, please. So that's a video. If you can play the video. Yeah. So here, what you see is crude oil and these materials. So the bolts which you have seen are materials out of recycled paper, and we have impregnated our gelator material in the right side material. Actually, the bolts. And after some time, you can see the whole of the crude oil is absorbed and gelated or congealed by this material. The left side is a control where you don't have the gelator, only the cellulose bolts are there. So cellulose bolts alone cannot do this job. You need this gelator which is impregnated and which will make it. You can go back to the normal slides. So another interest in our group is, as I said, the orderness gives property to polymers. And I also told in normal solution phase chemistry, when you make polymers, you get a random polymer, you don't have an order. So to get order, we want to use the self-assembly principle, which I have just shown. Using weak interaction, we assemble this kind of monomers. The double-shaped material is called a monomer, actually. So we have some motifs which can undergo some self-assembly due to some non-covalent interaction. So they self-assemble like a chain through this weak non-covalent interaction. Now also you can see two heads, actually, a blue head and a red head on either side of this dumbbell. And these are mutually complementary reactive motifs. That means if they come closer, they will react automatically and they form a covalent bond, a strong bond. So we designed such molecules with this mutually covalent motifs, and we assemble them. Then by which we will make them at proximity. This blue head and red head will be at proximity. Then they will automatically react and they will make a much more stronger covalent polymer. But due to the process of this self-assembly, we get an ordered structure. So this can be done in gel and also in crystal. Crystal is also a self-assembled system. So such reactions due to this proximity in packing is called topochemical reaction. So we use topochemical polymerization. In other words, I make monomers in such a way that this azide and alkane is one of these mutually complementary motifs we are talking about. They are close enough in the crystal lattice, then they will react automatically to give a polymer of the crystal upon mild heating or even at room temperature. Can you go to the next slide, please? So you don't need solvent, you don't need catalyst, you don't need anything. Just you make the monomer and crystallize and sometimes heat, sometimes nothing. So this is the reaction we are interested in, that is the azide alkane cycloaddition reaction. So this reaction, why we are interested, this reaction has a high thermodynamic drive, actually. The product is a triazole at the right hand bottom side. So that is called triazole, which is 65 kilocalorie per mole. In the formation of this one from the azide and alkane, it will release about 65 kilocalorie per mole. It's an exothermic reaction. Now, nevertheless, there is a high kinetic barrier, actually. There is about 20 kilocalorie to reach the top of the hill, or you call transition state. Once it reaches there, it will automatically react. In a normal solution in flask, you don't get this kind of arrangement unless you have catalyst or other modes of activation. But in crystal, it is possible to have this kind of arrangement or close to this kind of arrangement, close to the transition state-like arrangement. Then it will react automatically to give the product in the crystal. Such reactions we are doing in crystals, actually. We call it as topochemical azide alkane cycloaddition reaction or TAC reaction. Next slide, please. So this is the first molecule we have made. This is a galactose sugar-based molecule having an azide and an alkane motif. These are mutually complementary material. You can see two pictures of this crystal's photograph after 30 minutes and after 40 days. They look very similar morphologically, but they are very different, actually. One is monomer, the other one is reacted at room temperature. Even at 0 degrees, this reaction happens without doing anything. You make the monomer crystal, after some time you have the polymer crystal. And you can isolate some of these oligomers if you stop the reaction in between, and you can find that in all these cases you have a very conserved one-fold triazole linked dimer, actually, trimer, tetramer, etc. Next slide, please. So this is the crystal structure. You can see as expected this azide, which is marked in blue dotted bolts actually. This azide and alkane, and which is shown as a black dotted bolts. So they are at proximity and they are very ready to react, about 3.6 to 3.3 angstrom between them, and they are just ready to react in the crystal lattice. And they are also packed in a linear fashion, in a linear fashion in the sense in a head to tail fashion, and they can undergo polymerization. So after some time, if you do the crystal structure again of the same crystal, you find that all of this azide and alkane is vanished, but you have triazole in the right side of the picture actually. So it's a single crystal to single crystal transformation, which happens at even at 0 degrees centigrade. Next slide, please. So can we design such reactions? So we have relied on Cambridge crystallographic data center. All these crystal structures are reported. All of them have this peculiar dihydroxy motif in them. This shown as in red OH groups. And because of that, all of them form this kind of a specific zigzag hydrogen body. Next slide, please. So we want to make, next slide. We want to make such a material which has this diol motif, this dihydroxy motif, and this azide and alkane. This is what is expected based on the literature data. Next slide. Yeah. So this is what is expected as a fibril. You can see hydrogen bonded fibril. And because of this packing, what is expected is this azide and alkane will be at proximity in the crystal lattice. Then we can do reaction. I mean, just by heating, it will undergo reaction along this direction. You get a glycopolymer. Next slide. So this is what the crystal structure. We made the material crystal is here. This is the zigzag hydrogen bonded assembly is there as expected, and also that is making the azide and alkane at proximity 3.3 angstrom unit between them, just ready to react. And upon heating, next slide. Upon heating, this undergo complete crystal to crystal, single crystal transformation. You get a polymer. This is the polymer structure. Next slide, please. So we have increased the complexity. We have made even from disaccharide. This is a disaccharide trallose. So we have attached the azide and alkane at these hydroxyl groups, and we have, next slide. We have done reaction using this disaccharide. We got two different crystals actually from different solvent system. Both of them react. Next slide, please. And both of them react to about more than 90%. I mean, close to 100%, and you get polymer of this more complex disaccharide. Next slide, please. And this is an interesting case. We have made this mannitol-derived monomer, which gives two polymers in a single crystal. You are making a blend in the single crystal. So in the polymer, in the crystal structure, you find that on the right side, the packing, the molecules are self-sorted. There are two different kinds of monomers, I mean, two different conformers actually. And each of them are self-sorted, and one conformer react with only that kind of conformers, and another conformer react with another kind of conformers. And they form different linkages. In one case, it is 1,4 linked triazole linkage, and in another case, it's 1,5 linked triazole linkage. So in effect, what you get is a mixture of 1:1 mixture of two different polymers in a single crystal. This is very interesting actually. So next, of course, is nucleic acid. Can we do this in make it DNA, for example? Again, the CCDC data. This is all reported data. For example, this cytosine derivatives. This known in literature, and all of them undergo this kind of dimerization and this kind of tape-like hydrogen bonded structure. This we want to exploit for making DNAs, for example. Next slide. So this is what we want to make. We want to make a cytosine derivative with 5' and 3' substitute as azide and alkane. The molecule structure is at the bottom. If you do that, we will be able to make this kind of DNA wherein you don't have phosphodiester, much more stable triazole linkage, and we can make such DNA material. Next slide, please. Yeah, this material we have made, and next slide, please. And this is the packing as expected. The azide and alkane are at proximity, and this is the NMR actually of the monomer and the polymer. It's completely polymerized after some time. Next slide, please. And this is another one. This is another DNA analog wherein you have an extra benzene, and because of that, this interaction is much more stronger. The interaction of the non-covalent reaction, they are ready to react again. Azide and alkane are at proximity and are ready to react conformation. Next slide, please. About 3 angstrom units. So, and it reacts in a single crystal fashion. This is the structure of a DNA wherein you don't have a phosphodiester. It's a DNA mimic. Next slide. So next is, of course, protein. Can we make proteins? Again, the idea is here. So we make some sequence wherein it form either bit sheet, parallel or anti-parallel. In either case, you have the head and tail talking to each other. That is known in the literature. In the beta sheet-like peptides, the head and tail will talk to each other. So, of course, next slide. So, of course, our head and tail is, of course, the azide and alkane. Then we will be making them at proximity. Then we can do reaction along this direction, and we can make pseudoproteins. Next slide, please. So we have done several protein-like molecules. This is the first dipeptide we have taken, having valine alanine system. As you can see below, the crystal packing, azide and alkane are at proximity, ready to react, and upon heating, this reacts to about 90%. Next slide, please. And that gives about 7 kilodalton sized protein-like molecule. And one interesting thing we have found here is this crystal, after some time, show some kind of twisting actually at room temperature. And if we do NMR of this one, we found that some percentage is reacted already even at room temperature. Now, if we heat a fresh crystal, below bottom structure I'm talking about, C and D, fresh crystal, after a few minutes you can see the twisting. Of course, always it is twisting to the right-handed helical fashion. Obviously, the question is, do the chirality has any say in the nature of twisting? To address that, we have made, next slide please. To address that, we have made the enantiomer, the mirror image of this one, and DD peptide, for example, and we found that in that case it is going to the opposite side. This is the first time anyone has shown that the molecular chirality has definitely a say in this kind of a direction of twisting. Next slide, please. So we can do this reaction in gels. This is a gel actually. This in the gel also. We can do the same reaction. You don't need to crystallize. Making crystal is not that easy. I mean, if you are talking about a lot of crystal, you cannot make a lot of crystal, I mean, kilograms of crystal, but you can definitely make kilograms of gel. So in gels also, this kinds of reaction you can do. This is what we have shown in this picture. Next slide, please. Next, yeah, this is another system, diphenylalanine, again known to form this kind of beta sheet-like structure. So we wanted to see whether this can polymerize. Next slide. Yeah, so this we have made, and we found that yes, this is also forming beta sheet-like structure. And right-hand top right-hand side, you see the packing diagram. You see the azide and alkane are at proximity, but not in a ready-to-react information. Nevertheless, it reacts. When you heat at about 60 degrees centigrade, it reacts. And the structure at the bottom you see is of the polymer. You see there is something new. So two dots actually, so two red dots at every place. These red dots are nothing but water. So during the polymerization, it takes water from the atmosphere, sucks in water from the air actually. So that's very interesting. Next slide, please. This is again single crystal reaction. And this water goes, if you heat this material, it goes below 50 degrees centigrade. Even at room temperature, if you will blow dry air, the water can be released. And this is very much reversible. We have shown at least 30 cycles of hydration, dehydration with this crystal. And you can solve the crystal structure with water or without water. So the interesting thing is this water absorption. Such materials which can take water reversibly from the atmosphere are interesting for atmospheric water harvesting. There is a lot of water, at least 6 times water present in river bodies, that much water is present in the atmosphere actually. Now people are looking for materials which can take such atmospheric water for harvesting. People are usually looking at coves and mainly morphs actually, but the problem with morphs is of course water can interfere with the metal center. So this is a pure polymer, pure organic polymer, which can take reversibly water about 8.28%. And the relative humidity is also very good actually. Even at 30% of relative humidity, it can take water. So that means even in Gulf countries, this material can take water. Next slide, please. So we all know packing dictates property. These all are different forms of carbon, diamond, graphite, fullerene, example. So all of them have different properties. The property it depends on its packing. So can we do different packing for polymers? Next slide, please. So this is a question which is already existing, but I want to solve this one. So we thought, yes, we make different polymorphs of this monomer actually. So we got 3 different polymorphs of this particular dipeptide monomer, and you can see they have 3 different structures actually. In this, the first case, it is an anti-parallel orientation. I mean, if they form polymer, you get an anti-parallel change between adjacent change. And the second one, you get parallel change, and third one also parallel change, but there is difference between the two, because in one case, there are 2 different kinds of conformers actually. So essentially what I am saying here is we got 3 different packing or 3 different polymorphs of the monomer, and by polymerizing that, we got 3 different polymorphs of the polymer actually. So that's very interesting actually, and all of them have different properties which we are currently studying. Next slide, please. So yeah, so another topology is another interesting thing. So we were interested in polyglycines. This is a sequence which is present in, for example, in natural silk. So there are 2 different packing for the polyglycine. This is the first one is polyglycine 1. There is a normal lamellar packing. The other one is polyglycine 2, which is a hexagonal packing. The hexagonal packing is much more stronger. So we thought by mutating some of this the peptide bond with this triazole bond using our tag chemistry, what will be the fate of this kind of polyglycine? So we want to make this monomer on the left side bottom and right side bottom. I mean both of these monomers and see their fate. So next slide, please. So we made, this is the dimer, and in this case what we got is again ready to react conformation between azide and alkene, 3.3 angstrom unit, and it automatically reacts. At room temperature it reacts. In this case we get a cross-laminated topology. At the right hand bottom you see the cross-laminated adjacent layers of these polymers are at right angle to each other. This is very interesting topology for a one-dimensional polymer. Next slide. And similarly, it's a higher derivative, that is a tripeptide, also behave very similarly. This also undergoes crystal to crystal transformation at room temperature. That monomer transforms automatically, evolves automatically to a polymer, and that also gives cross-laminate topology. Next slide, please. This is the cross-laminate topology I'm talking about. If you stack a wood like this, that is a cross-laminate topology. This is the topology we got, and we got very interesting properties also because of time I'm going. This is another topology, novel helix topology, which we have got with another peptide. So this is an amyloid structure on the left side. Usually amyloid structure has this kind of beta sheets stacking together. And recently Lando reported a close alpha amyloid, wherein alpha, we have made another topology wherein we have a two-stack topology. Next slide, please. Yeah, so finally to summarize, I have shown you what is a tag reaction, topochemical azide alkane cycloaddition reaction. We have done this kind of reaction to make polymers of sugars, different sugars we have polymerized, all of them I cannot talk about, technical problem. Also, we have made polymers of a nucleoside to make DNA mimics, and we have made different kinds of protein-like molecules, very huge molecules, and with different properties actually. All of them, again, I could not talk to you. And also, I have shown you our work on gels for a different application, for example, soft optics, and also for oil spill recovery. Finally, go to the last slide, please, to thank my students who have done all this work. These are the top guys are already graduated from the group. The bottom one is my current group. And finally, thank you all for this your time and also for this opportunity. And I'm really sorry for this way actually it happened. Thank you.